Okay, let us come back here to this chapter number 10. Good morning, good afternoon, good evening, and good night to all of you. Hope everyone and pray everyone that are doing well and fine. So today I'm going to talk about chapter number 10, which is as you see in the screen, the title on heteroskedasticity. Right, that particularly will be the chapters that we are concerning about today, and going to discuss for you today about the heteroskedasticity. So this particular chapter is a continuation from the previous chapter, which is on autocorrelation. Now we are heading towards the end, which is chapter number 10 on heteroskedasticity. So what is heteroskedasticity? And the question that we asked in the previous chapter, what is the issue here? What are the consequences? How to detect and how to solve the problem will still be the question in mind for this particular chapter of heteroskedasticity. Pronounce with me, right? Heteroskedasticity. All right, so in this chapter, certainly again, you're interested to answer this following question. What's the nature of heteroskedasticity? All right, and the second part will be what's the consequences if there is heteroskedasticity present in the regression function, in your regression result. How to detect and what's the remedial measure? Let's say you have the problem when you detected in, number 3. What should we do? Right? Should we follow the strict SOP, or should what sort of solution that's supposedly to be done? All right. So we start off with the question number 1. What's the nature of heteroskedasticity? So one of the assumption actually in the CLRM, again, let's go back to this particularly when we talk about assumption, which is in chapter number 4. We still remember, certainly go back to chapter number 4. We have this assumption, equal variance. Assumption number 4 actually are heteroskedasticity. This is heteroskedasticity. Let me put in red color. Equal variance is called heteroskedasticity. All right, let's go back to this particular chapter. So we assume that the variance of the error term must be homoskedastic. In that sense, is equal or constant variance over the sample that you have, right? Over the sample that we have. Right? If the error do not have a constant variance, our regression function is said to have a problem of heteroskedasticity. Right? So either you have this hetero or you have homoskedastic. Homoskedastic means the same. Heteroskedastic state means that not the same in terms of the observation. And I have given you some example when we talk about chapter number 4. Certainly previously, we talk about how actually heteroskedasticity are actually associated mostly with cross-sectional data. Autocorrelation is with time series data. Right. For example, you have a big, medium, large firm, low income, high income, and so on and so on. We have the B40, we have the M40, and then you have the T20. Right. Here in particularly in Malaysia. So that give the example of how we actually perhaps if you have different income level and how we consume, how's the pattern of expenditure would be different. But here we assume that the regression function have a constant variance. All right, so there's no room for heterogeneous types of differences among the income among the income families, right? In this particular sense, if that is what we call as heteroskedasticity. So this is the example in graphical format. This is the example, or in picture format. This is homoskedastic. Same all the three, right? Here it's not the same because it's accordingly to what we have and what we earn and what we can and willingness. So again, assume that in the regression function, the error is homoskedastic rather than heteroskedastic. That's number 1. That's the nature of heteroskedasticity. Now we go for number 2. What's the consequences of having heteroskedasticity? If heteroskedasticity present, the OLS are still unbiased, but the problem exists where in the variance, because it's no longer the true variance, because the variance is no longer constant. So it will impact the blue properties becoming inefficient, and then the test of significance might be invalid and they are no longer blue. Means that they are unbiased, but they are not efficient. Certainly, they are not consistent, and they will affect the result. And it will the result will be questionable in that particular sense. If you still remember, these consequences actually are similarly to autocorrelation. Let us go to that particular chapter. Right? Let's go to chapter number 9. Let me put side by side so that you can see it clearly. Actually, right? You could see it clearly, right? This is the consequences actually are the same, pretty much the same. If you see here, right? The consequences are the same. All right, the consequences of having both actually the same. I put side by side like this. Right, put side by side like this, you can see clearly autocorrelation and heteroskedasticity having the same consequences of if you have the problem of either one of the problem or both in that particular sense. All right, so let us go back again to chapter number 10. So that's the consequences. That is number 2. So now we moving forward to the next part, which is detecting. How to detect? Like in autocorrelation, you have a method called Durbin-Watson, you have a method called Durbin-H, and you have a method called Bruch-Grotfi LM test. Here in heteroskedasticity, you have this test. We call it, the first one is called BPG, Bruch-Pagan-Grotfi. I added up a pagan there. Other than the BG test, it's just Bruch-Pagan-Grotfi. This is the page number you can find for the textbook of Gujarati and Porter. Right? This method, this is the steps of doing it. You run the regression or estimate the regression, obtain the residual, test for the residual, and construct based on the variance, and then you construct it based on this formula, and then after that you run the auxiliary regression. After that, you will find out whether it's a reject or do not reject with the null hypothesis that we have, assuming that the null hypothesis here is no heteroskedasticity. So if you reject, means that you have a problem of heteroskedasticity. All right, so this is it. Okay, using the chi-square. So the idea here is that while you construct the variable p defined as this one, which is simply the residual squared divided by the variance, and then you estimate the regression, obtain the residual, again you check back and you compare with the chi-square that we have. So it's a bit complicated because you have to do two regression. First regression, you transform it, and then based on the formula, you construct a new variable, and then you regress it, and then you only check. It's a little bit complicated in that sense. White general test is much more general. In that sense, we call it white general. White general test, and this is available in Eview. The first one just now, BPG, is not available in Eview. So this is the one that we're going to do. Right? Estimate the regression, obtain the residual, run the following regression, which is from the residual perspective, and then under the null hypothesis of no heteroskedasticity, it shows that the sample size times the R square obtained for the auxiliary regression, step number 2, whether it follows the chi-square, and from there you just compare, and you see that if it's reject, you have a problem of a hetero. If not, then you do not have a problem heteroskedasticity. So n times R square, that's the formula, more simplified compared to the BPG just now. All right, so this is the next steps. So no hetero and heteroskedasticity exists. Right, so that is the two way of doing it. I mean, certainly we're going to show. I'm going to show you using Eviews for the second way, which is the white test here. The next one, the next section will be the fourth section here. We're moving to the fourth section, which is actually very fast indeed. In that in that particular sense. All right. So there are three measurements or three remedial measures that can be used to solve the problem of heteroskedasticity. The first one, we call it weighted least square, right? When the variance is known and the variance is unknown. And then the second one is re-specification of the model. This is sounds like when I ask you to do in chapter number 7, especially refer back to your chapter number 7, when I ask you to do the 5 different model, and then you choose the best one. And the 5 different model, you use the CV method, choose the best one. So re-specification, you change the specification of the variable, the functional form of the variable. You might solve the problem. The third one is white heteroskedasticity corrected standard error. This is available in Eviews, number 3, which again, it can show you, right, in that sense. So here, weighted least square is when there are two cases there, when the variance is known and the variance is not known, right? Assuming that the true variance is this one, and then to remove heteroskedasticity, we just divide all variables by this, by the variance. So you transform the equation, right? Just transform this equation. So you have a new equation, new data set. New data. You put it in Eviews, run again the regression, and check again whether you have the problem. So that's number one here. But in reality, we do not know the real value of the variance. And the error term variance is proportionate perhaps to this one or proportionate to the other one, or is either like this or is either like this. So that kind of a proportionate perhaps. So when it's unknown, right? When it's unknown, case number A, when it's unknown, the error is proportionate to like this, right? This is how it looks like. Proportionate means that they are more linked to the x2 here in this sense, right? I'll show you the example here. In this sense, assuming the variance is proportionate to x2, only then we transform the regression base to x2, right? So you transform like this. The variable is like having the function, if you still remember, 1 divided by x in our the 5 different model, right, of the log linear, linear log, and then you have reciprocal. This is like reciprocal. You transform them, then you regress it again. After transformation, you put a star there to ensure that this is a new regression, and then after that you check back again with heteroskedasticity test to ensure that you don't have the problem. All right, so that's what it can be done. The second one is that when it's also when it's unknown, but case number B, right? This time around, almost the same case. It's just that other than proportionate just now using the punca causa like this, we just divided by the x itself, right? Again, you transform a new one, and then the new regression, you get the new results, and then you compare again the result back to check again for heteroskedasticity. Right? It's like the same thing as of right now the swab test, the first swab. If you are being suspected for having COVID-19, the first swab to test, whether you have that kind of, you have the COVID-19 virus, and you have the second swab, right? So it's same thing. You need to check few times to ensure that the virus is not there. So same thing here. After you regress, you re-regress means that re-specified the model divided by the case just now, either by like this, right, or square root of x2, or you divide it just straight away with x2, and then after that you transform it for new regression, estimate them, and check again another time for heteroskedasticity to confirm that issue has been solved. The second solution is that we could choose a different functional form, whether it's logarithm, whether it's a linear log linear, or reciprocal in that sense. A reciprocal, we can go back to the first model just now, to the first solution. All right? All right, so this is one of the solution, re-specification. So that is why, as I told you, functional form here is very important, most important here. This is available in Eviews, right? The method actually corrected standard error by taking into consideration of heteroskedasticity without changing the value of estimated coefficient, right? It's only changing means that it's already corrected in that sense, the standard error for heteroskedasticity. I'll show you this one, right? So that is the 3 methods of solving this, and we are at the end here of the slide. So perhaps I can go and show you actually how we're going to do it in Eviews. Again, I'm doing this part like this, Eviews here. I'm going to show you right now, right? Right now we go for Eview. Eview number 10. I'll use back the data that we use for the manufacturing GDP, that data, this data set. Continue on with what we have. Select GDP, export manufacturing. Open as an equation straight, not as a group. Estimates, this is what you get all this time, like the previous chapter also. All right. The next one we should do, write down the command there, check for hetero. For heteroskedasticity. Right, check for heteroskedasticity. Where we go? We go view. Same thing, we go residual. Same thing, you have heteroskedasticity test there. Click on that. There's a lot of solution there. As I said just now, and earlier on, the earlier version, I should rephrase my statement. The earlier version of Eview do not have BPG, but here you have BPG. Right, here you have BPG. So let us see what BPG result will show us. This is the result from BPG. Heteroskedasticity test of Bruch-Pagan-Godfrey test. We can check on the F statistic, or either you can use this one or the other one. Right? You use F, no problem. Although in the slides it was suggested to use chi-square. But what we have here in Eview is F test. So we use F test, no problem at all. The F test suggested that you do not reject. BPG suggests non-existent of hetero. Right, that is good. Non-existent. So let us confirm with white test. Go back to residual, go back to heteroskedasticity, go back to white, click OK. See, this is interesting. White test suggests the presence of hetero. One suggests no, one suggests yes. This is a rather interesting observation. So what should we do if we have this kind of different dimension of result? What should we do? Should we go for another one? Can try another one. Perhaps the one that's not been exposed to you, right? This one, you can try on this one. Arch, autoregressive conditional heteroskedasticity. Try on this. This shows that, right, the arch test shows that at 5%, you do not reject. Means that no issue of hetero. So at least as of now, based on what we have here, BPG suggests non-existent. White test suggests heteroskedasticity. Arch suggests no problem of heteroskedasticity. 2 against 1, eh? 2 against 1 in that sense. So most of the time we can do this simple statistics in that sense, majority in that sense. But certainly, if let's say we follow white test suggestion, then we should solve the problem. How we solve the problem? There are 3 methods as I've been discussed here in the slides. Actually, the first one is using weighted least square. This one could be done manually inside the regression. You can regress the regression and divide it by the, let's say, x2, or divided by the variance and so on when the case is known in that sense, right? This when is known, the variance is known, the true variance is known, and true variance is unknown, right? And then you have re-specification, means that you change the model. Here we use linear model again. How about log linear? How about linear log? How about double log model? We have not done that yet, right? The next one will be, the next method available will be the white heteroskedasticity corrected standard error. This is available in Eview. Let me show you here. Okay, use this one. That white heteroskedasticity method specification. You can always do that part here. The coefficient, the covariance, right? This. Let me go back here. White heteroskedasticity, right? The way which is actually available also here. Let me show you here. Right. Here, like specification. Right. Click OK on this. Right. This is so-called one of the solution. Assuming that it solves the problem if we use this method, although actually the third method available out there, which is also available in Eview here, what heteroskedasticity corrected standard error, right? This is so-called the method that is available there. All right. Okay. So here basically this is what we have, ordinary, or you want to go by this one. So there's a lot of this is another one. White, Hinsky, heteroskedasticity, consistent standard error, and covariance. These are all the options there. Either you do Huber-White, HSC, HC here variance, various, right? McKinnon, H2 here. This is a few options that you have, including this one, right? So the 3 options there, which is available inside Eview actually. You can do the Huber-White, the HIC, or the HC itself. Yeah, not this one, because we have to specify the cluster. All right, so go back here. This is the original result, and that one is the result that is already been transformed in that sense, particularly using this method, right? Taking into consideration of heteroskedasticity without changing the value of the estimation. Okay, so this is what we have in Eviews, and how to solve it, right? Let me go for number 2, right? How are we going to solve it? How to solve the issue? So, method suggested are divide by the first method there, which is called weighted least square. The second method is which is available is called re-specification, the functional form. Right, the functional form. You can change the functional form. And the third one, which is available in Eview, is what where you go for the estimates here. You go for the option. You can choose from here the covariance method. There are few there, right? The white heteroskedasticity, white hetero, right? City, white heteroskedasticity corrected standard error, right? So these are the few which is available that you can use to solve the issue. All right. So again, thank you very much for watching this video. I hope everyone still staying safe, stay healthy, certainly. And I'll see you in the next particular chapter, and certainly when we do the online class of this particular chapter. Can't wait to have that. I have additional actually notes available in Ellipse, which is this one. I put up this one. I also put up some others like this one also. I will talk about this one in particular, especially in the class after we do all the 5 different model and the diagnostic tests, and then we will discuss further in the class. All right. For time being, thank you very much again. I'll see all of you in the next video. Adios and bye bye. Take care. Ciao.